Your program is running fine. Two threads are doing their jobs, then everything stops. No crash, no error, no log message. The program just hangs there frozen doing absolutely nothing, and it will stay that way forever unless you kill it. This is a deadlock. It is one of the most frustrating bugs in all of concurrent programming because the code looks correct, the logic looks sound, but the system locks itself into a state it can never escape. Today we are going to visualize exactly how that happens, why it happens, and how you fix it. So what actually goes wrong? Imagine two threads running at the same time. Thread A grabs lock M and then tries to grab lock N. Thread B grabs lock N and then tries to grab lock M. Thread A is waiting for N. Thread B is waiting for M. But thread A holds M and thread B holds N. Neither one can move forward. Neither one will ever release what it holds. Both threads are stuck waiting forever. That is a deadlock. Two threads, two locks, zero progress. Before we go further, we need to understand what a lock actually is. A mutex lock is a token. Only one thread can hold it at a time. When thread 1 acquires the lock, it gets exclusive access to the shared resource. Thread 2 and thread 3 both want in, but they have to wait. When thread 1 is done and releases the lock, one of the waiting threads gets it next. Locks exist to prevent data corruption from concurrent writes. The problem is not the lock itself. The problem is how multiple locks interact when threads acquire them in different orders. To really understand deadlock, look at it as a graph. Draw 4 nodes, thread A, thread B, lock M, and lock N. Thread A holds lock M and wants lock N. Thread B holds lock N and wants lock M. Now draw the arrows. You get a cycle. Thread A points to lock N, which points to thread B, which points to lock M, which points back to thread A. That cycle is the deadlock. It is not just a metaphor. This is literally how operating systems and databases detect deadlocks at runtime. They look for cycles in the resource allocation graph. Computer scientists identified exactly 4 conditions that must all be true simultaneously for a deadlock to occur. These are called the Coffman conditions. First, mutual exclusion. A resource can only be held by one thread at a time. Second, hold and wait. A thread holds at least one lock and is waiting to acquire another. Third, no preemption. You cannot forcibly take a lock away from a thread. Fourth, circular wait. A cycle exists in the wait graph. Remove any single one of these conditions and the deadlock becomes impossible. That is the key insight behind every fix. When a deadlock happens in a running system, how does the runtime detect it? The process has 3 steps. First, build a wait for graph by mapping which threads are waiting for which locks. Second, run cycle detection on that graph, typically a depth-first search looking for back edges. Third, if a cycle is found, the deadlock is confirmed and the system kills or rolls back one of the stuck threads to break the cycle. If no cycle is found, the system is healthy. Database engines like Postgres and MySQL do this automatically. The Java virtual machine exposes it through thread mxbean. The single most effective prevention strategy is consistent lock ordering. If every thread in your program always acquires locks in the same global order, a circular wait can never form. The bad pattern: thread A locks M then N, thread B locks N then M. The orders conflict and a deadlock is possible. The fix: both thread A and thread B lock M first and then N. Now no matter how the threads interleave, they can never form a cycle. This one rule eliminates circular wait entirely and costs you almost nothing. Beyond lock ordering, there are 3 more powerful strategies. Try lock with timeout. Instead of blocking indefinitely, attempt to acquire a lock for a maximum duration. If it times out, release everything you hold and retry after a backoff. This breaks the hold and wait condition. Lock hierarchy. Assign every lock a global priority number and always acquire locks in ascending order. This is a formal version of lock ordering that scales to large code bases. Deadlock avoidance. Use the banker's algorithm, where the system only grants a lock if doing so keeps the overall resource state provably safe. And for the highest performance scenarios, lock-free data structures using atomic compare and swap operations eliminate mutexes entirely, making deadlock structurally impossible. Deadlocks appear in every layer of real systems. In databases, transaction A locks row 1 and transaction B locks row 2, then each tries to lock the other's row. Postgres detects this via its 2-phase locking system and kills the younger transaction automatically. In the OS kernel, a process holding the disk lock wants the network lock while another process does the reverse. The kernel's scheduler detects this through its internal wait-for graph. In Java, 2 synchronized blocks nested in opposite order across 2 threads is the classic nested monitor deadlock. The JVM's thread mxbean.find deadlock threads method surfaces these at runtime so you can diagnose them in production. If you take one thing away today, deadlock is not random and it is not mysterious. It requires all 4 Coffman conditions simultaneously. Break circular wait through consistent lock ordering and you have eliminated the most common class of deadlock in one line of reasoning. For the rest, add try-lock timeouts as a safety net. Write the wait for graph on a whiteboard when you are debugging a hang. The cycle will be there. Thanks for watching.